Hello, everyone, and welcome to part two of Mechanical Ventilation 101. We're going to first start out with the how, which is how we ventilate. So, a few ventilator basics. First of all, your ventilators need to be plugged into a 50 psi outlet. Both inspiratory and expiratory limbs of your ventilator need to have filters on them. And as well, your circuit setup is important to take note of that. So, the circuit setup is such that everything after the Y connection makes the circuit functional. So in this particular case here of the ventilator, we have a flow sensor, we have an HME, which is a heat moisture exchanger, we have a side stream and tidal CO2 monitor, as well as the inline suction, which a lot of people are used to seeing. Keep in mind that everything that we've added after the Y is added dead space to our circuit. So it's important to take note of that. This is a short video on the circuit setup in the research room. All right, now this is the face of the ventilator. I've divided it into three sections, the one being the LCD screen, two being the hotkeys that provide a little bit of quick actions, and three being the rotary knob, which allows you to navigate the LCD screen. If we take a look at the layout of the ventilator, of the screen, it's important to note that when you see the screen at the top, your ventilator is actually not ventilated. It's in standby. If you see the screen at the bottom, that means that your ventilator is ventilating the patient. Let's take a look at the waveforms section. So what do you see and where do you see it on the screen? For nurses for charting, most of the information you're going to require is going to be placed in the zones 1, 2, and 3, which are your modes, your control parameters or your settings, and the monitor parameters. So in taking a look at modes, what we see here is that this displays a mode of ventilation. So regardless of the mode of ventilation that you're in, keep in mind that your ventilation actually, when we put someone on a ventilator, what we're trying to achieve is oxygenation and ventilation. By that I mean supplemental oxygen and carbon dioxide removal. We achieve our supplemental oxygenation via PEEP and FiO2. Now, PEEP is the positive end expiratory pressure, and its main goal is actually to improve your functional residual capacity, therefore improve your surface area for gas exchange. FiO2 is supplemental oxygen added into the air the air that's being delivered to the patient. Ventilation is achieved by CO2 removal, specifically by minute ventilation, which is a function of tidal volume and respiratory rate. Now, this is where we have a conversation about dead space, in that the actual part of the air that is partaking in gas exchange is just your alveolar ventilation. Your minute ventilation is divided into your alveolar ventilation and your dead space ventilation. Everyone has a little bit of dead space ventilation, and we can measure that or estimate that by using the formula 2.2 mLs per kilo. Example, on a 50 kilogram patient, with a 50 kilogram ideal body weight patient, know that at least 110 mLs of their tidal volume will not be expired and therefore not participate in gas exchange. We can worsen this by adding to the circuit. So all those functional additions that we put on the circuit to make our circuit functional actually add dead space, and we call that mechanical dead space. So how do you tell what mode you're on when you take a look at your ventilator? Because that's what it's important for a nurse at the bedside to know. If you're on a spontaneous mode, you look at top the top right of your screen. What you're going to see is the mode is going to be written there. As well, you can tell because there are little triangles that will show patient effort. However, this can be misleading, especially if you have other things that are triggering the ventilator when it's not actually the patient. And you also have a respiratory rate, because in spontaneous modes, we do not set a respiratory rate. Typical spontaneous modes are pressure support and adaptive support ventilation. Of course, there are risks like asynchrony and apnea. If you are in a controlled mode, you can take a look at, again, the top right side of your screen. It will be written there. And keep note that you now do not have those little triangles that show patient efforts. So settings, when we set a ventilator, when we put our settings into a ventilator, we take note of what type of mode that we're in. Are we pressure ventilating or volume ventilating? If we're pressure ventilating, it's important to note that because we're controlling the pressure, we allow the volume to vary. And if we are volume ventilating, because we're controlling the volume and thereby controlling the flow, we allow the pressure to vary. So what you set into the ventilator is going to be different. So in pressure modes, we'll actually set a pressure. We'll set an inspiratory time, we set a respiratory rate, a PEEP, and an FiO2. In volume modes, we set a tidal volume, we set a flow or a waveform, and we set a respiratory rate, PEEP, and FiO2. There are hybrid modes that you actually see a lot with this ventilator because those are the controlled modes that come with it, called APV CMV. In these modes, not only do we set a tidal volume, we actually set an inspiratory time as well. And we set a pressure indirectly by setting a pressure limit. Our alarm becomes our pressure limit. So we are still pressure ventilating in this case, but trying to target a particular volume. Your monitor parameters are any information that you're getting from the patient. So peak pressures, respiratory rate, things along those lines. Keep in mind peak pressures, which is fairly important. We'll come back to that in the alarm section. If you want to see more monitored parameters, you hit the tab at the bottom left that says monitoring, and you can get information from there. And finally, waveforms. So depending on the mode you're in, waveforms are going to be specific to those modes. So if you're in a pressure ventilating mode, you can expect that because of your flow or your volume is varying, the flow waveform is the one going to look more like what the patient is, or the disease state of the patient. So for instance, if you have um, a COPD who is gas trapping, you find that in the flow waveform, we say they are not coming back to baseline. So on the expiratory phase, which is where the arrow is pointing to on the right picture, you are finding that it won't be coming to baseline. It won't be coming back to the 0 point, in which case we say you're gas trapping. Other things you can tell from your waveform is that if you have a coarse flow waveform, it could be that you have secretions or condensation in the tube. Now, if you're in a volume mode where we allow pressure to vary, the pressure waveform is what is telling us about our patient's disease state. So, for example, you could have a COPD patient where you have high peak pressures, and you will see that in your pressure waveform. We do not typically use volume modes, especially on the T1 ventilators, because they do not carry volume modes. All right, so let's go through a little quiz. Ventilators can be attached to a flow meter. That is false. Filters are required for both inspiratory and expiratory limbs of the ventilator circuit. That is true. Ventilation can occur when the standby screen is visible. That is false. Mechanical dead space is everything on the circuit after the Y connection. That is true. Minute ventilation is a function of tidal volume and respiratory rate. That is true. Patients with obstructive disease can be expected to have elevated peak pressures. That is true. And the quick short answer, what is the purpose of PEEP? To improve your functional residual capacity and calculate the anatomical dead space of a 70-kilogram patient. Remember, we're using 2.2 mLs per kilo, 154 mLs. All right. So moving on, when do we actually intervene? So this table will be made available to you. I don't want to go through the entire table, but it is important to pause here and read through the table so that you understand what common alarms that you may run into, the limits that those common alarms are usually set to, and then the common causes of that and how to troubleshoot them. One common troubleshooting, or I guess cause and therefore troubleshooting, is to check your cuff pressure. Make sure that you do not have a leak. And here's a short video that actually shows how we check a cuff pressure. So we inflate the cuff and we want to maintain it between 20 and 30 centimeters of water. Now, if you have secretions, going through a few common alarms, if you have secretions, if your troubleshooting does not work, it's really important that you are able to troubleshoot, or you're able to know what the next steps are. Now, if you have secretions, the common solution is to suction, right? So we're going to go through the steps to suction, and then we'll go through other common alarms as well. So to suction, apply 100% FiO2, and you can do that by hitting one of the hotkeys, which will be the increase FiO2. So you turn the suction control on to 150 millimeters of mercury. You connect the suction tube into the closed system and advance the catheter until the patient coughs. You pull back a little bit. This is really important. You need to make sure you're pulling back 1 to 2 centimeters before you start applying suction, because you don't want to cause trauma to the carina. Now, there's a short video that talks about the inline suction system, which I'm hoping you guys would have watched prior to this. So if you suction or you troubleshoot and it does not work, here's something that you can do. And this applies to any alarm. If you have any alarm, you troubleshoot, it does not work. First of all, please call respiratory therapy. And if your patient starts to deteriorate, and by that I mean your SATs start to drop, or you start having a lot more PVCs, or something catastrophic is actually happening, in which case you'll have to switch to a bag valve mask in this particular order. So place the ventilator in standby, and you do that by hitting the power button once and then hitting the activate standby tab. Let's go back into here. Disconnect the circuit, connect to the BVM. So connect the BVM to the endotracheal tube and squeeze the bag and watch for chest rise. Now, to maintain a rate of at least 12 breaths per minute, which is 1 breath every 5 seconds. If your patient is on a PEEP of more than 10, a PEEP valve is recommended, and respiratory therapy will make sure that your BVMs do have a PEEP valve attached. Keep in mind that we're still going to continue to have Q2 checks, ventilator checks, if we have a patient in the emergency department as per our ventilator policy. Again, a common alarm, low minute ventilation. If your troubleshoot does not work, same drill, place your ventilator in standby and switch to the BVM. Again, standby by pushing the power button once and then the activate standby tab. So let's go through our last quiz. There are only four ventilator alarm settings. That is false. There are actually more, but the ones that are shown in that table are the most common ones, and therefore I thought those would be the ones that you should keep in mind. Low minute volume and loss of PEEP alarms can both be caused by a circuit disconnect. That is true. To resolve a loss of PEEP alarm, just silence it. That is false. Don't ever just silence alarms and leave them unless you know why you are silencing that alarm. There's the reason why I did not talk about the silence button on the ventilator, because I want to make sure we're not encouraging anyone to just hit silence and leave the ventilator. Pressure limit alarms can be caused by asynchrony. That is true. Lastly, if troubleshooting steps do not work, what is your next step? Call respiratory therapy, and then follow the troubleshooting steps that are outlined. That concludes this lecture. This will be followed by a hands-on section. So if you thought you were done with me, unfortunately, no. Um, so I'll see you all at the bedside by a ventilator, so that we can put what we've learned here into practice. Have a good day.